Ensuring that the information provided is accurate and up-to-date is paramount. It is also crucial to cover a wide range of topics within the electrical field and to provide practical guidance and real-world examples. I am an experienced electrical engineer with a strong understanding of the field, and I am willing to provide guidance and answer questions on various aspects of electrical engineering, including electrical theory and principles. This encompasses fundamental concepts like Ohm's law, which states that voltage equals current times resistance, expressed as volts equals amps times ohms. Understanding Kirchhoff's laws, including Kirchhoff's current law, which states that the total current entering a junction must equal the total current leaving the junction, and Kirchhoff's voltage law, which states that the sum of all voltages around any closed loop in a circuit must equal zero, is equally vital. The concept of power, calculated as voltage times current, is also important, where power is measured in watts. We can delve into alternating current and direct current circuits, impedance, reactance, and power factor correction. Furthermore, the principles of three-phase power systems and their advantages over single-phase systems can be discussed. Regarding electrical components and systems, a broad understanding is required. This includes resistors, capacitors, inductors, diodes, transistors, and integrated circuits. Each component has a unique role in circuit behavior. For example, resistors limit current flow, capacitors store electrical energy, and inductors oppose changes in current. We can examine various types of transformers, including step-up and step-down transformers, and their applications in power distribution. Understanding the operation of motors and generators, including alternating current induction motors and direct current motors, is also essential. Discussions about different types of cables, conductors, and wiring methods will be beneficial. Delving into protective devices such as circuit breakers, fuses, and ground fault circuit interrupters, also known as GFCIs, is important for safety. We can examine lighting systems, including incandescent, fluorescent, and light-emitting diode, also known as LED lighting, and their energy efficiency. The design and analysis of electrical systems is also a key area. This includes load calculations to determine the required capacity of electrical services and feeders. Conductor sizing based on ampacity and voltage drop calculations is crucial and can be done using the National Electrical Code, also known as NEC Table 310.16 as a reference. Short circuit analysis to determine the available fault current is essential for selecting appropriate protective devices. We can explore grounding and bonding techniques to ensure electrical safety. Understanding the principles of power distribution systems, including radial, loop, and network configurations, is also beneficial. Furthermore, designing control systems for various applications, such as motor control and lighting control, is an important aspect. For electrical installation and maintenance, knowledge of proper wiring methods and techniques is critical. This includes understanding the requirements of the National Electrical Code. Performing inspections and testing of electrical systems to identify potential problems is important for preventative maintenance. Troubleshooting electrical problems using appropriate tools and techniques is a valuable skill. We can discuss maintaining electrical equipment such as motors, transformers, and switchgear to ensure reliable operation. Implementing safety procedures to prevent electrical accidents is paramount during installation and maintenance activities. Electrical safety and codes are of utmost importance. Understanding the National Electrical Code, which sets the standards for safe electrical installations, is crucial. Adhering to lockout/tagout procedures to prevent accidental energization of equipment during maintenance is essential. We can discuss the proper use of personal protective equipment, also known as PPE, such as gloves, safety glasses, and arc flash suits. Recognizing electrical hazards such as shock, arc flash, and electrocution, and taking steps to mitigate those risks is vital. Furthermore, understanding grounding and bonding requirements to minimize the risk of electrical shock is crucial. In terms of electrical troubleshooting, using appropriate test equipment such as multimeters, clamp-on ammeters, and insulation testers is essential. Reading and interpreting electrical schematics and wiring diagrams is a valuable skill. We can discuss troubleshooting techniques for various electrical problems such as open circuits, short circuits, and ground faults. Analyzing circuit behavior to identify the root cause of problems is important. Furthermore, repairing or replacing faulty components to restore proper operation is necessary for effective troubleshooting. To supplement your learning, take advantage of textbooks, online resources, and industry conferences. Seek mentorship from experienced electrical practitioners to gain valuable insights and guidance. Get involved in hands-on projects or internships to apply your knowledge in real-world settings. Network with other electrical professionals to expand your knowledge and career opportunities. And most importantly, stay curious and enthusiastic about the field of electrical engineering. One should refer to the National Electrical Code, or NEC, for specific requirements related to electrical installations. For example, NEC Section 210.12 covers arc fault circuit interrupter, or PSI protection, while NEC Section 250.50 addresses grounding electrode systems. It is also important to understand the different types of overcurrent protection devices, such as circuit breakers and fuses. Circuit breakers are designed to trip when the current exceeds a certain value, protecting the circuit from damage. Fuses, on the other hand, are designed to melt and break the circuit when the current exceeds a certain value. When selecting overcurrent protection devices, it is important to consider the ampacity of the conductors being protected and the interrupting rating of the device. The ampacity of a conductor is the maximum current that the conductor can carry continuously without exceeding its temperature rating. The interrupting rating of an overcurrent protection device is the maximum fault current that the device can safely interrupt. In addition to overcurrent protection, it is also important to provide ground fault protection. Ground fault protection is designed to detect and interrupt ground faults, which can be caused by insulation failure or other problems. Ground fault circuit interrupters, or GFCIs, are commonly used to provide ground fault protection in residential and commercial buildings. GFCIs are designed to trip when they detect a small amount of current leaking to ground, typically 5 mA. It is also important to understand the different types of wiring methods that are permitted by the NEC. Some common wiring methods include rigid metal conduit, or RMC, intermediate metal conduit, or IMC, electrical metallic tubing, or IMD, and non-metallic sheathed cable, or NM cable. Each wiring method has its own advantages and disadvantages, and the appropriate wiring method for a particular application will depend on a number of factors such as the environment, the type of occupancy, and the cost. In addition to understanding the NEC, it is also important to be familiar with other relevant standards such as those published by the Institute of Electrical and Electronics Engineers, also known as IEE, and the National Fire Protection Association, also known as NFPA. These standards provide guidance on a wide range of topics such as power system design, electrical safety, and fire protection. For example, IEE Standard 1584 provides guidance on arc flash hazard calculations, while NFPA 70E provides guidance on electrical safety in the workplace. Staying up to date on the latest codes and standards is essential for electrical engineers. This can be done by attending industry conferences, reading technical publications, and participating in continuing education courses. Continuing education is particularly important as it allows electrical engineers to maintain their competence and stay abreast of new technologies and best practices. In addition to technical knowledge, electrical engineers also need strong problem-solving skills. Electrical systems can be complex, and it is important to be able to diagnose and troubleshoot problems quickly and effectively. This requires a systematic approach and the ability to think critically. Electrical engineers also need good communication skills. They must be able to communicate technical information clearly and concisely to both technical and non-technical audiences. This is important for collaborating with other engineers, working with clients, and presenting technical information to decision makers. The field of electrical engineering is constantly evolving, and it is important to be a lifelong learner. This means being willing to learn new things and adapt to changing technologies. It also means being willing to seek out new challenges and opportunities. By continuously learning and growing, electrical engineers can stay at the forefront of their field and make a valuable contribution to society. Moreover, to add on the initial points, electrical theory and principles are the foundation of electrical engineering. It encompasses the knowledge of basic circuit laws, such as Ohm's law, which, as previously stated, is voltage equals current times resistance, and Kirchhoff's laws. These laws are fundamental to understanding how electrical circuits work. We can also explore complex impedance, which is the opposition to alternating current flow, combining resistance and reactance. Reactance is the opposition to alternating current flow due to capacitance or inductance. The concept of power factor, which is the ratio of real power to apparent power in an alternating current circuit, and power factor correction techniques to improve energy efficiency are important as well. Understanding the characteristics of alternating current waveforms, including sinusoidal, square, and triangular waves, and their applications is also useful. Furthermore, the principles of electromagnetic induction and the operation of transformers are essential. In addition to basic circuit theory, a solid understanding of semiconductor devices such as diodes, transistors, and integrated circuits is crucial. These devices are the building blocks of modern electronic systems. We can also discuss digital logic circuits, including gates, flip-flops, and microprocessors. These circuits are used in computers, control systems, and other digital devices. Another important topic is control systems engineering, which deals with the design and analysis of systems that control the behavior of other systems. This includes feedback control systems, which use feedback to maintain a desired output. For example, a thermostat is a feedback control system that maintains a desired temperature. Electrical components and systems are the practical building blocks of electrical engineering. This includes a wide range of components, such as resistors, capacitors, inductors, transformers, motors, generators, switches, relays, and connectors. Each component has a unique function and characteristics. Resistors limit current flow, capacitors store energy, and inductors oppose changes in current. Transformers step up or step down voltage, motors convert electrical energy into mechanical energy, and generators convert mechanical energy into electrical energy. We can also examine electrical systems, which are combinations of components that work together to perform a specific function. Examples of electrical systems include power distribution systems, lighting systems, motor control systems, and communication systems. Power distribution systems deliver electrical power from a source to various loads. Lighting systems provide illumination for various spaces. Motor control systems control the speed, torque, and direction of electric motors. Communication systems transmit information from one point to another. The design and analysis of electrical systems involves applying the principles of electrical theory to create functional and reliable systems. This includes load calculations to determine the required capacity of electrical services and feeders. Conductor sizing to ensure that conductors can safely carry the required current. Voltage drop calculations to ensure that the voltage at the load is within acceptable limits. Short circuit analysis to determine the available fault current and select appropriate protective devices. Grounding and bonding to provide a safe path for fault current and minimize the risk of electrical shock. Protective device coordination to ensure that protective devices operate in a coordinated manner to minimize the extent of an outage. The design and analysis of electrical systems also involves considering factors such as safety, reliability, cost, and energy efficiency. Electrical installation and maintenance are essential for ensuring the safe and reliable operation of electrical systems. This includes proper wiring methods and techniques to ensure that conductors are properly connected and protected. Inspections and testing to identify potential problems before they cause failures. Troubleshooting to diagnose and repair electrical problems quickly and effectively. Maintenance of electrical equipment to prevent failures and extend the lifespan of equipment. Safety procedures to prevent electrical accidents and injuries. Electrical safety and codes are of paramount importance in the electrical industry. The National Electrical Code, or NEC, is the primary standard for safe electrical installations in the United States. The NEC covers a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. In addition to the NEC, there are other relevant standards, such as those published by the Institute of Electrical and Electronics Engineers, or IE, and the National Fire Protection Association, or NFPA. These standards provide guidance on a wide range of topics, such as power system design, electrical safety, and fire protection. It is also important to be aware of local electrical codes, which may be more stringent than the NEC. Electrical troubleshooting is the process of identifying and repairing electrical problems. This requires a systematic approach and the ability to use various test equipment, such as multimeters, clamp-on ammeters, and insulation testers. The first step in troubleshooting is to gather information about the problem. This includes asking questions about the symptoms, the history of the equipment, and any recent changes. The next step is to visually inspect the equipment for any obvious problems such as loose wires, damaged components, or burned insulation. After the visual inspection, the next step is to use test equipment to measure voltages, currents, and resistances. This can help to isolate the problem to a specific circuit or component. Once the problem has been isolated, the next step is to repair or replace the faulty component. After the repair, it is important to test the equipment to ensure that it is working properly. Taking advantage of textbooks, online resources, and industry conferences can greatly benefit your learning. Textbooks provide a comprehensive foundation in electrical engineering principles. Online resources such as websites, videos, and online courses offer a wealth of information on various electrical engineering topics. Industry conferences provide opportunities to learn from experts in the field, network with other professionals, and see the latest technologies. Seeking mentorship from experienced electrical practitioners is an invaluable way to gain practical knowledge and guidance. A mentor can provide insights into the real-world challenges of electrical engineering and offer advice on career development. Getting involved in hands-on projects or internships is a great way to apply your knowledge and gain practical experience. Hands-on projects allow you to design, build, and test electrical systems. Internships provide opportunities to work alongside experienced engineers and contribute to real-world projects. Networking with other electrical professionals can help you expand your knowledge and career opportunities. Networking can be done through professional organizations, industry events, and online communities. Staying curious and enthusiastic about the field of electrical engineering is essential for continued learning and growth. The field of electrical engineering is constantly evolving, so it is important to stay up to date on the latest technologies and trends. This can be done by reading technical publications, attending conferences, and taking continuing education courses. By staying curious and enthusiastic, you can continue to learn and grow throughout your career.